Today we're going to do something special. We're going to take a look at a device. Not just any device, but a data center that fits on your desk. I'm talking about the Dell Pro Max with GB10, and for those of you who don't know it, GB stands for Grace Blackwell, which means that this device contains the most recent GPU and CPU chips from NVIDIA. We're going to go through everything that you need to know about this device, starting with the unboxing and the setup, discussing hardware details, and then we're going to take a look at a bunch of different playbooks from NVIDIA, but also use cases that I'm personally going to use this device for, like running inference on huge models, generating images locally, playing around with robotic simulations, and also fine-tuning models. And all of this, of course, runs on Linux. This is going to be super exciting. We're going to cover a lot. If you like this video, let me know by hitting the like button and subscribing. But now, let us get right into it. Alright, so we're going to talk about this beautiful device right here, the Dell Pro Max with GB10, and I need to mention for the sake of transparency that Dell and NVIDIA sent this device to me for free. So this is what I got in exchange for making a video about it. I was not paid money, so this is not a typical paid promotion where I'm getting sponsored by someone to talk about the product. They sent this to me for free. That is what I got in exchange, and my review here of this device is going to be an honest review, and I'm going to share my experience with it. So let us start by briefly talking about the difference between the Dell Pro Max with GB10 and the DGX Spark. Now, to keep it simple here, I'm not going to go into all the details. The basic idea is that NVIDIA developed the DGX Spark, which is kind of a reference model. So this is the thing that they build as a reference product, and the companies can then go and build their own version of that. So the Dell Pro Max with GB10 is Dell's version of the DGX Spark. Now, a couple of specs here. The device that I have has 4 terabytes of SSD disk space, a Grace Blackwell 10 super chip with 20 cores, and 128 gigabytes of shared memory. So basically memory that is shared by the CPU and the GPU. And this thing brings 1 petaflop of FP4 compute onto your desk. The system has an ARM CPU and a so-called unified memory architecture. This means, as I already mentioned, that the CPU and the GPU share the memory, so they act as one system when it comes to the memory. No copying back and forth is necessary, but of course this memory is not the same as VRAM. VRAM is much faster, but in this system we have 128 gigabytes, which allows us to run pretty large models. This brings us to the next point, which is who this device is actually for. This device is not optimized for speed or throughput. It is optimized for developers and for the NVIDIA ecosystem. So this device is perfect for developers who want to use the NVIDIA stack and the NVIDIA ecosystem. Think of it to be a little bit like a mini data center on your desk, and if you get something to work on this little device here with the NVIDIA stack, you can basically take that proof of concept, this prototype, and you can scale it up and integrate it seamlessly in a proper data center, because that is the same technology, the same architecture, and the same ecosystem. So the main use case for this device is to bring the Blackwell chips to you at home so you can work on them, you can build stuff with them without needing to access data centers. The device itself comes with DGXOS pre-installed, which is basically Ubuntu, but already set up perfectly for working with NVIDIA's ecosystem. But also in general, you can use the system to run inference on pretty large models locally. So you can run models with up to 200 billion parameters using these 128 gigabytes of shared memory. And you can also do fine-tuning, of course. So the focus is clear: size and ecosystem over speed and throughput. This is a device for developers, not a high-speed computing machine. Now let us go through the setup process and a bunch of different use cases. So this is the box that was sent to me. When you open it, on the left side from your perspective, you will find a box with user manuals and some cables, and on the right side is the device itself. The first cable that we find here is the high-speed connector for the QSFP port. This cable can be used to connect 2 such devices together with a high-speed connection that has 200 gigabits per second. Then of course we also have the power supply and the 2 cables that belong to that. And then in the white packaging there is the device itself, the Dell Pro Max with GB10. The most interesting part is probably the back. There we have the high-speed QSFP connection that I talked about. This is where you use the cable to connect it to another Dell GB10 device. Here you should use the left port, not the right port. Then we also have an Ethernet port with 10 gigabit per second, an HDMI port for connecting a monitor, as well as 3 USB-C ports with 20 gigabits per second and an additional USB-C port for powering the machine. The front looks well designed, and there is also an LED that will show us when the device is turned on. So here I already connect the power supply to the USB-C port, and you can also see that the QSFP cable actually belongs into this port. As I said, put it into the left side. The user manual tells us that we can set up the device either by remotely connecting to an access point or by doing it in the classic way and setting up everything with a monitor, keyboard, mouse, and so on. Of course, I prefer the classic way, so here comes my messy setup. I first connect the Ethernet port, then a monitor, and I use a special USB to USB-C adapter to connect my wireless mouse. My keyboard already connects directly with USB-C. Then I press the power button and wait for the system to boot up. We can see the Dell logo for a while, and then we see the message, "Welcome to the Dell Pro Max with GB10. To get started, we choose some basic settings like language, keyboard layout, and time zone. We accept the terms of use, and we create our user account. After this, we need to wait for a while for the system to be installed and updated. Once this is done, the system reboots and we can log into our account. As you can see, this is a special version of Ubuntu made for the NVIDIA ecosystem, and we can see that this is Ubuntu by running NeoFetch. After the initial installation, I chose to use a more comfortable setup, so I used a small desk. And now we can move to screen recordings. I installed OBS on the system for recording, and getting started with it is extremely simple. On the official NVIDIA website for DGX Spark, you can find a ton of playbooks. Playbooks are basically tutorials where you just have to follow the instructions, copy commands, and you can get stuff done easily. For example, to get started, I followed the playbook for installing VS Code. This one is the simplest and takes only 5 minutes. We just have to scroll, copy and paste commands, and then we end up with VS Code running locally on the device. But we don't have to be working on the device directly at all. We can use a tool called NVIDIA Sync to connect to the device from our host system. There's also a tutorial about this on the official NVIDIA website, but the process is quite simple. Depending on your operating system, you follow a different process for the installation. In my case, I installed 2 packages from the AUR. Then you need to figure out the IP address of the device. For this, just run a hostname command. And once everything is installed, you can easily connect to the system via NVIDIA Sync using the hostname. After all of this, we can then easily use the system remotely. For example, we can open up a terminal. We can also just run VS Code and work remotely on the machine. Or we can access the DGX dashboard where we can see the GPU utilization and the memory usage. Here we can also launch a Jupyter Lab instance. In this case, we have all the packages and all the CUDA dependencies already set up and installed properly. So if we use PyTorch, we can see that we have a GPU available. One of the easiest and also most useful things to do is to set up OpenWebUI with Ollama to have your own local version of ChatGPT. For this, you'll also find a playbook on their website. We can open up a terminal to connect to our machine, add our user to a group, and pull a Docker image. Then we can create a custom application in NVIDIA Sync. For this, we only need to provide the correct port, in this case 12,000. We can name this OpenWebUI. And we have to provide a launch script, which we can copy and paste from the playbook. Then we can just click on this custom application now, and it should open up the OpenWebUI. The first time it might take a bit longer, afterwards it should be quite quick. We have to register for a local account, and then we can start pulling open source models, for example GPT-OS with 20 billion parameters. As you can see, we can easily chat with it, it answers quite quickly, and it also generates code. In the dashboard, you can always monitor GPU utilization and system memory usage. Since we have a lot of memory, we can also pull the larger version, which has 120 billion parameters. This also works without any issues. Setting up Ollama directly is also not an issue. Just make sure to provide the correct host, which would be 0000, and then you can just target your Dell system as an API server when coding in Python. Connecting OpenCode to it is also easily possible by just editing the config file. This way we can easily do agentic coding without having to pay for any API usage. If you want to do local image generation, that's also possible. You just have to follow the playbook for installing Comfy UI. Again, if you don't want to think about this, you can just copy and paste the commands here. This will result in a Comfy UI setup using Stable Diffusion 1.5, but there's no reason to stay with this model. You can also just go to Hugging Face, download any other model that fits into the hardware, and then use that instead. Here you can see how I use a newer version of Stable Diffusion to create images of dogs. Now, since this device is optimized for NVIDIA's ecosystem, let us see how easily we can set up IsaacSim and IsaacLab. For those of you who don't know what these are, IsaacSim is basically a simulation environment, and IsaacLab is built on top of IsaacSim and allows us to do reinforcement learning with robots. Last year, I made a video about this on my channel, but my hardware in my desktop PC was not strong enough to run IsaacLab and IsaacSim, so I had to work in a cloud environment that NVIDIA gave me access to, but this time I should be able to do it locally because I have this mini data center. For the setup, I again just simply follow the playbook. I copy and paste the various commands that are provided here without thinking about it too much. And there you go, I have IsaacSim running on this system without any lags. So if I knew how to do 3D modeling, which of course I don't, I could now start and do some interesting stuff. But I'm more interested in reinforcement learning, so let's set up IsaacLab on top of it and see if we can run the training processes that we ran in the previous video. And without any setup issues, I'm able to run the cart pole reinforcement learning and also the humanoid trying to learn to walk. Finally, for the last playbook example, let us see how we can fine-tune local models using Unsloth. For this, I'm going to only follow part of the playbook tutorial because I already have a notebook where I did some fine-tuning with Unsloth before, also a video on my channel. So I'm going to follow the instructions to set up everything with Docker, but then after running the test script, I'm going to set up my own environment with UV to run my JupyterLab instance. Here, it's very important that we provide the proper index for PyTorch so it supports CUDA. Once everything is set up, I can just run my notebook and it fine-tunes a model on my own dataset. I can also evaluate it and see that it actually worked. Now, what's also good about this system is that NVIDIA is continuously pushing updates. They want to keep supporting this and making this a go-to device for developers. Just recently, they pushed a DGX Spark software update with better power efficiency, with more support for TVs and monitors, as well as for Bluetooth sound, and also with expanded security controls. So NVIDIA really makes it a priority to support this line of systems. So now we looked at a lot of different use cases and playbooks, but what am I going to be using this device for? One, I'm definitely going to use it for local inference or inference with local open weight models. So if I just want to save money, or if there is something that requires a certain level of security, I don't want to share the data with anyone else, I'm going to be using this machine to run a powerful local model with up to 200 billion parameters. Two, I'm going to be using it for experimentation and prototyping when I'm doing development. So either for my startup or for some other side project, maybe I need to test a workflow. I need to know if I can rely on open weight models instead of using professional providers that charge money. And to test this out before I actually commit to it and build a system around it, I'm going to be using this device to see if it actually works as a proof of concept. Three, I'm going to be using it for research and experimentation when my hardware on my desktop system is not powerful enough. For example, I'm currently working on EEG experiments with a doctor from London, and there we need to fine-tune pretty large models that just don't fit on my GPU in my desktop PC. So I'm going to be using this device to do the experiments and thus also the research. Also, as I mentioned, in my startup, I have a lot of AI use cases, and trying stuff with open source models to see what we can do without having to pay providers is a very useful thing, and also pushes the boundaries by allowing me to do research with state-of-the-art open weight models. Four, I'm going to be using it to test newly released NVIDIA technology. So if NVIDIA releases a new software stack, a new part of their ecosystem, this is the best device in order to test it. If I want to see how it works, if I want to see if I can build something around it, that is the perfect piece of hardware to do that. And five, I'm not sure about this one, but maybe I'm going to use it as a portable data center. So if I move somewhere for a while, I might take it with me to have the computation power without having to carry around a huge computer. I can basically put it into my laptop bag and also take a portable monitor with me, and I then have a data center to go. So yeah, let's come to a conclusion. I think this device is a very powerful device for prototyping, for development, for playing around with stuff, especially if you want to work with NVIDIA's stack, with NVIDIA's ecosystem. That is the perfect device for that. It's not optimized for speed. It's not optimized for throughput. You can do inference and you can fine-tune very large models because you have 128 gigabytes of shared memory. So this is a perfect system for developing, prototyping, and doing proof of concept type of work, especially if you're focusing on the NVIDIA ecosystem. So if you like this video, let me know by hitting the like button and subscribing. In the description down below, you will find a couple of links that might be interesting to the playbooks and to the device itself, about the device itself. And besides that, don't forget to subscribe and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.